Okay, so let's write the Maxwell's equations in medium. Now let's just remember what we did in medium. Okay, first we had defined some quantity called the polarization, and this polarization was the electric dipole moment per unit volume. And then we said that this polarization we can describe as some kind of a charge density. It corresponds to a volume charge density given by minus the gradient of P, and also a surface charge density, which was the normal component of P. So instead of dealing with properties of the material, medium, instead of dealing with this polarization, we can just work with rho and sigma, the charge densities. And then we have the magnetization. Magnetization also corresponded to magnetization we defined as the magnetic dipole moment per unit volume. And we had also seen that we can describe the magnetization as some kind of a current density. JB, which was the curl of M, and surface, which was, I don't remember the sign now, M cross N, N being the normal vector. So instead of working with magnetization, we could work with the surface, the bound current densities. Well, these currents, they should also be, well, they actually correspond to some physical currents in our system, in the material, so they should also be conserved. So let's see, divergence of JB. Well, this is 0 already because JB is the curl of some vector field. So you see that we don't really need a rho, let me call rho MB. So there is no current, there is no charge density corresponding to a magnetization. But you see, there will be a current density corresponding to the polarization. And the reason is that, you see, what do we mean by polarization? You apply some external electric field, the charges are moving, but the moment that you say that they are moving, there is a current density in our system. There should be some current density corresponding to the motion of this polarization. And you see, from this equation, we see that d rho b by dt, this is equal to minus divergence of del p by del t. I just took the time derivative of both sides. But this tells me that del rho b by del t plus the divergence of del p by del t, this is equal to 0. Well, if the polarization is changing with time, so it's just the charges, the polarization is nothing but the displacement of the charges. So as the displacement is changing, the particles are moving up and here and there. So there's a current created. And since this any charge density should be conserved, so this is our current density corresponding to polarization. Let us just call it Jp. So this is the current density corresponding to polarization. So instead of working with magnetization and polarization, we can work with bound current density, bound charge density, and polarization current. And now we can just write down our Maxwell's equations. You see, we know that the divergence of the electric field was equal to rho over epsilon 0, but now we also have a bound rho, so this is minus divergence of P over epsilon 0, which tells me that divergence of epsilon 0 E plus P, this is equal to rho. Well, this was what we had defined as D, the displacement field. This is one of the equations. Well, this is in fact exactly the same equation that we had derived when we were looking at electrostatics in medium. Then we have the curl of E is equal to minus del B by del T. Well, nothing changes. There's no current. There's no charge densities here. So everything stays as it is. And then we have the divergence of B is equal to 0. Again, no modification, because there is nothing that contributes, no current or no charge densities that contributes to the divergence of B. And now finally we have curl of B, which is equal to mu 0. Well, this was mu 0 J. But if we are talking about in matter, there is also an additional contribution to the polarization. We have the polarization current plus mu 0 del P by del T. Plus, well, there's also this current due to the magnetization, mu 0 curl of M. Plus mu 0 epsilon 0 del E by del T. Sorry, here I made a mistake. It is epsilon 0 E plus P. Well, let's see, this is the curl of B over mu 0 minus M. This is equal to J plus del over del T epsilon 0 E plus P. Well, this was what we had defined as our H field, and this is what we had defined above as our D field. So the curl of H is equal to J plus derivative of the displacement field with respect to time. Well, let's just collect them all. We have the divergence of D, this is equal to rho. Divergence of B, this is equal to 0. Curl of E, this is equal to minus del B by del T. And curl of H, this is equal to J plus derivative of this displacement field with respect to time. Well, you see, this is in fact where the name displacement current probably comes from. You see, this displacement current is nothing but derivative of this displacement field with respect to time. This is our displacement field. That is in matter. So that's kind of all we need to know about electromagnetic theory. The rest will be, all our next semester will be just the application of this law, of these equations. So how do we create light? So how does these cellular forms work? How do we transmit energy? How do we guide electromagnetic waves from one point to the other point if we want to guide them? And we will see that if you have solved that problem in your midterm, if you calculated the unit of mu 0 epsilon 0, the unit is 1 over the velocity squared. So 1 over square root of mu 0 epsilon 0 is basically the speed of light in vacuum. Then we will study how light behaves in medium. So these are our equations. So how does light behave in medium? Why does it diffract, reflect, etc.? How does it behave in conductors? So that's all about next semester. Now, any questions up to this point?
Peki bu noktada relativite ile ilişki var mı?
Up to this point, not really. But you see, for example, you have probably studied in your modern physics course, you have seen the Lorentz transformations, right? Lorentz transformations were derived before Einstein's theory of special relativity. Those are the transformations that leaves the Maxwell's equations invariant. So if you change your coordinates based on the Lorentz transformations, in terms of new coordinates, Maxwell's equation looks exactly like this. Nobody knew why until Einstein, but Lorentz had derived them just looking at Maxwell's equations. Sorry, before that. Okay, I claim that 1 over mu 0 epsilon 0 was the speed of light. That was kind of the starting point of special theory of relativity. So the question is, okay, we are talking about the speed, but the speeds are always relative to reference frames, at least in Galilean relativity. Then what is the speed? So here we derived kind of the speed of light, but with respect to which reference frame? So for a long time, people just said that, okay, these equations are actually correct in a special reference frame in which something is at rest, and that something is called ether. So they thought for a long time that there was ether filling the universe, and the electromagnetic waves are nothing but if you just think about ordinary waves, you have the waves in the sea, which are not just the motion of the water molecules, or you can think of waves on a wire. These are just the motion of the medium. In this case, it is the wire. So what is the medium of electromagnetic waves? They thought that, okay, the electromagnetic waves is the motion of this ether. And there is a special reference frame in which the ether is at rest, and this speed of light is the speed of light in the reference frame of the ether. But if that was the case, you see the Earth is moving in a circle. So relative to Earth, ether should be moving at different speeds, at different directions, and at different times. So then the next thing you do, let's measure this change in the speed of light. So that was the basic idea of Michelson and Morley, to measure the difference in the speed of light in different directions. So if there is ether, then you see if you are moving in this direction, for example, let's say you are moving in the direction of ether. If you are moving in this direction, you are moving perpendicular to ether. So your average speed of light moving back and forth along this direction will be different than the average speed along this direction. And that difference, ideally, we should be able to measure. And then the experiment didn't find any difference. So that was kind of, okay, it wasn't immediate, but that was the final nail in the coffin of this ether theory. So then there's no ether.
Peki Maxwell bunları nasıl yazmış?
Well, you see, Maxwell added this one. All the rest were before Maxwell. The contribution of Maxwell is this term. And they were, up to now, we were all based on experiments. You see, the Gauss law is just experiment, the force of attraction between two wires, two charges. That is what this law is about. This law, we derived it from, the magnetic field created by studying the magnetic fields created by wires. This is how we obtain this one in the lab frame, somewhere on Earth. And then this law, again, it was experimental, but the first derivation, if you remember, are motional EMF actual experiments on Earth, in some other place on Earth, probably. And then, no, not that one. That one is, again, the observation by point charges. This is by the study of the magnetic field created by current-carrying wires, at least this term. And up to this point, nobody referred to any velocities. And then you add this term also, the Maxwell, for the consistency. Again, no reference to any reference frame, no reference to any velocity. But kind of out of the blue, you end up having the speed of light. So that was kind of the problem. Nobody mentioned any reference frame up to that point. But then how do you talk about a speed without a reference point, reference frame? So that was a puzzle. And then once the ether theory was gone, what Einstein said was, okay, the speed of theory is the same in every reference frame, which is against Galilean relativity. The relativity that we learned in first year is the Galilean relativity. And he obtained his modified equations how the velocity changes from reference frame to reference frame. You see, the Galilean relativity is basically based on the fact that, on the assumption that measurements in every reference frame are the same. The distance, the length in every reference frame are the same. So you have this addition of velocities, etc. But then you cannot have any speed constant in every reference frame. They have to change. So Einstein had to give the concept, we had to give the concept of the length to be the same in every reference frame. The length measurements between two events can change from reference frame to reference frame. So that's why in every reference frame we can measure the speed of light the same.
Hocam, bunun spekülasyon olmayan herhangi bir yorumu var mı şu an? Popüler olan, en güncel şekilde. Yani sadece ışık hızına evrensel bir sabit demek yerine hani bunun sebebini açıklayan herhangi bir popüler teori var mı?
Well, let's say the laws of physics have to be the same in every reference frame, including Maxwell's equations. That's another way of saying that the speed of light has to be the same. Because it just, at least if you take this Maxwell's equations as correct in every reference frame, then the speed of light is a law, essentially. The speed has to travel at that speed, the light. Now, why is Einstein's theory of relativity correct? Or why is Newton's equations correct? Well, they're basically the same question. It would be interesting to have an answer, but we don't have one.
Işığın elektromanyetik dalgalar şeklinde yayıldığını Maxwell'dan mı?
Those electromagnetic waves, again, we will discuss next year, next semester, sorry. So we have enough time, I hope, to solve my example. Let's consider a point charge moving at constant velocity. Let's look at this point. There is an electric field there. Let's say it is at a distance r. Let's just call that distance r. Well, there's an electric field. This is my small r. And that electric field is constantly changing. So there should be a magnetic field there. So what is that magnetic field? So this is, let's say, a positive charge plus Q. Well, you can just treat it as more or less as a current along that straight line to determine the direction of the magnetic field. Just use your right hand. The magnetic field lines at that point will be just pointing out. Somewhere over here it will be pointing in. It will just make circles around V, around the velocity, around this axis, around the trajectory. So this is the direction of B. No. At that point, this is the direction of B, and at this point, this is the direction of B. And we have rotational symmetry, etc. So let's say this is the Z direction. B will be equal to, it will depend on R. It will also depend on time t. And it will depend on Z. And it will be in the phi hat direction.
Hocam büyük R yerine küçük R yazmanız daha mantıklı olmaz mı?
Well, you see, this is my small r.
O değişmiyor. O değişiyor çünkü.
Small r is changing. Okay. Oh, yeah. So, well, you see, I would rather put small r is constantly changing. I would rather write the magnetic field in terms of quantities that do not change with time. If I said small r over here, small r will be a function of time also. But capital R is not a function of time. So I just want these variables, these arguments, to be independent of each other. I will eventually replace everything in terms of, write everything in terms of that small r. But at least as arguments of my function, I want them to be independent of each other. Now I will just assume a circle around the z-axis. This is my circle. This is the direction of my loop. And I know that integral of B dot dl around that closed loop will be equal to mu0 epsilon 0 times the time derivative of the electric field integrated over the surface. Now let's start with B dot dl. Around the loop. Well, B is some component in the phi hat direction. dl, again, just use your right hand. This is the phi hat direction at every point. So dl is also in the phi hat direction. This is the magnitude in the phi hat direction around my loop. So this is 2 pi r times B. Well, kind of the difficult part will be how to calculate the E. The integral of E. Well, we can of course take, you see, we have this freedom of choosing the surface. The only constraint we have is that the boundary of the surface we have to evaluate the electric flux should be this red loop. Well, rather than taking my surface to be flat, this flat disk, I will just assume my surface to be kind of a sphere, a part of a sphere with center at the position of my charge. That is what I will assume. So this is my Q over here. This is my loop. Or let me, hold on. This is my loop. I just took it straight from the side. Let's say this angle is theta, which will of course be a function of time. I will take the spherical shape. Now, I will make this one approximation. I will assume that the electric field created by my charge is 1 over 4 pi epsilon 0 q over r squared in the r hat direction. Well, this is called the quasi-static approximation. It is good enough if the speeds are slow compared to 1 over square root of mu 0 epsilon 0. So basically, I'm assuming that the electric field doesn't really change when my particle is moving. It's not exactly correct because I know that changing electric field will induce a changing magnetic field, and this changing magnetic field will in turn induce an additional contribution to my electric field. So this is not exactly correct, but nevertheless, it's a good enough approximation because I know that the corrections will be proportional to epsilon 0 mu 0 times v squared. Epsilon 0 mu 0 is 1 over the speed of light squared. So you can calculate this correction if you want. It's an exercise, but let's just stick with this one. Now, this is the electric field. So at every point on this sphere, the electric field is straightforward, is just outside, pointing out. R is the same at every point. So basically, the electric flux through that area is just 1 over 4 pi epsilon 0 q over r squared times the integral of ds. The total surface of that patch of the sphere. Well, that is basically what we need to calculate. Well, I can use spherical coordinates to calculate that patch. This is 1 over 4 pi epsilon 0 q over r squared. Well, ds, the surface element in spherical coordinates for a surface on a sphere is r squared sine theta d theta d phi. Sorry. It's the radius of the sphere squared, which is r. You say this is r. So they cancel, this r squared cancel this r squared. And I have 1 over 4 pi epsilon 0 q. Well, the theta sine theta. Theta goes from 0 to theta of t. And the phi integral, phi goes from 0 to 2 pi and then times 2 pi. This cancels this one, I have a 2. So the electric flux is q over 2 epsilon 0. The integral of sine is minus cosine theta. And theta goes from 0 to theta of t. So this is equal to q over 2 epsilon 0, 1 minus cosine of theta of t. What is cosine of theta of t? Well, it is this length over r. Well, here I know r. So this length is r small r squared minus capital R squared. But you see, I would rather keep that length and call it, let's say, L. So cosine of theta t is q over 2 epsilon 0, 1 minus L over square root of L squared plus R squared. Oh, sorry. Now, the reason why I keep the L rather than small r is that dl by dt is minus v. Oh, sorry, minus. As dl by dt, my particle is moving along the z-axis. So as my particle is moving, if it has a positive speed, then L is getting smaller and smaller with time, so dl by dt is minus v. So that's what I will be using. And now we have everything we need. 2 pi r times b. This is b dot dl. This should be equal to mu 0 epsilon 0 d by dt of phi e. Or b is equal to mu 0 epsilon 0 over 2 pi r. Let's take the time derivative of this phi e. We have, well, first take the derivative with respect to L times dl by dt, because phi, the electric flux depends on time only through L. L depends on time. This is equal to mu 0 epsilon 0 divided by 2 pi r times q minus q over 2 epsilon 0. Let's take the derivative of that term. So the derivative of L is 1 over square root of L squared plus R squared plus L times the derivative of 1 over the square root is just minus 1/2 times twice L divided by square root of L squared plus R squared cube times dl by dt is minus v. This is equal to, well, epsilon zeros cancel, mu 0 over 4 pi q v over r times these two's cancel. I have 1 over small r cubed. You see, this square root of L squared plus R squared is R. So I'm taking out an R cube. What remains inside is R squared minus L squared. But you see, R squared minus L squared is nothing but capital R squared. So this R cancels one of these capital R's. And we are left with B is equal to mu 0 over 4 pi q v r over r cubed. Or let's see, this is mu 0 over 4 pi q times v times small r times sine theta divided by r cubed. Because you see, capital R is nothing but small r times sine theta. So let me just redraw it here to see it a bit more clearly. This is my charge moving with a velocity v. This is the length L, R. This is the angle theta. So this is the vector v. This is the vector, let's say, R. No. This is the vector R. And theta is the angle between the vector v and r. So B is just mu 0 over 4 pi q times the magnitude of v cross r divided by r cubed, because the magnitude of v cross r is the magnitude of v, which is v, the magnitude of the vector r, which is r, the times sine of the angle between the two. Well, the angle between the two is theta, sine of theta. And we had already said that the B vector is just B in the phi hat direction. This was how we define the B vector. Now, what is the direction of V cross R? phi hat. So you see, the magnitude of this B vector is the same as the magnitude of mu0 over 4 pi q v cross r over r cube. Well, the direction of this B vector, which is phi hat, is the same as the direction of v cross r. So basically, they should be the same vectors, these two vectors, v and mu0 over 4 pi q times v cross r over r cube. Because both of these vectors have the same magnitude, they are both pointing in the same direction, but those are the two things that define a vector. So if two vectors have the same magnitude and directions, they are equal. Well, of course, this is also changes with time because v is constant, but r is constantly changing with time. So we have a time-dependent B field, which will create which will induce an additional electric field to our quasi-static approximation. So here we had this quasi-static approximation, which was the electric field is time-dependent because the r vector changes constantly, which induced this magnetic field, and that magnetic field is also time-dependent, which will induce an additional electric field here, and that will be smaller than this one, and the magnitude will be smaller by a factor of v squared over the speed of light squared. So for moderate speeds, well, it's just negligible. And again, this expression we had seen before. We say when we were discussing the current created by the magnetic field created by a current carrying wire, we also said that that can be written as the sum of magnetic fields of point charges of this form. At that time, we had said that, okay, we cannot really say that each charge creates this magnetic field because a point charge is not a magnetostatic system. So here we see that it's a good enough approximation, but not exactly true. Because as I said, this B field will induce an additional electric field, additional time-dependent electric field, which will induce an additional time-dependent magnetic field, etc. So we will have this infinite series. And this will be for moderate speeds, for speeds much slower than the speed of light, this will be the dominant contribution to the magnetic field.
Yani her seferinde oluşan elektrik alan bu kadar manyetik alan mı olur?
No, I mean, you see, the charge is moving. The first approximation to our electric field is this quasi-static approximation. This is a time-dependent electric field. It induces a magnetic field. And that electric field induces this magnetic field. But this is also a time-dependent magnetic field. So this will induce an electric field, which I should add to my quasi-static approximation. So there will be a correction to here, which will be also time-dependent. And due to that correction, I should also add a correction to my B field, which will be a correction to this term. And essentially, I will get an infinite series. Let's see, where did I wrote it? Yeah. I will again get this infinite series. To the zeroth order approximation, there is an electric field, no magnetic field. This electric field creates a correction to the magnetic field, which creates a correction to the electric field, which creates a correction to the magnetic field, etc.
Şimdi hocam bu seriye bakınca manyetik alan elde edebilmek için ilk önce elektrik alana mı ihtiyaç var? Manyetik alanın ilk term'i 0 ama elektrik alanında bir term var.
Yeah, you see, these are my equations. these two terms couple the last two equations. So in principle, I have to solve all of them, both of them at the same time. That we will do next year. But there are also iterative methods of solving the solutions. So you just make some iterations to your solution. So what you do is, you start with some given value, some chosen value, let's say. You put those chosen values, the zeroth order approximation on the right-hand side, solve for the left-hand side. You obtain another solution. That solution you put on the right-hand side and solve for the left-hand side, etc. But there's, of course, these two other equations, this J term and the rho term. So I would rather get rid of those terms first. I would rather find an electric field corresponding to a given E, rho, and B field corresponding to a given J. So those will be my zeroth order. Just ignore these terms. The zeroth order approximation basically would be both of them are equal to 0. That's your zeroth order approximation. Solve for, if you have a J or a rho, solve for the corresponding E and B. So that is your zeroth order approximation. Well, in our problem, what I did was, well, the J is far away. So at the point where I'm interested in, there is no J, I solve for E. And once I define, let's say, a region. No, okay. Yeah, at my point, no. Well, I just solve for them, these two equations, rho. I had a rho, that's my zeroth order equation. In powers of V0 over C. That is kind of, let's say this is mu 0. I can write this as mu 0 epsilon 0 over epsilon 0. You say J over epsilon 0. And let's say this is 1 over C squared. In the limit that the speed of light is huge, negligible compared to the velocity, J is proportional to V. So in that limit, this term is 0. There is no contribution from that one. Plus I only have that term. So my zeroth order solution for that particular problem is that the divergence of E is equal to rho, which is this quadratic approximation, and B is 0. Because for small velocities, this is negligible. And well, I already ignored them. So that is why I had the B equal to 0 as my zeroth approximation. But if there was an uniform wire, let's say, infinite wire, current carrying wire, and the current was changing in time, in that case, my zeroth order electric field would be 0, but my B field will be non-zero because rho will be 0 everywhere. But J is non-zero, so I get a non-zero B, but 0 E. It depends on your problem. Okay, so thanks for the semester. So this was kind of the last lecture of this course, at least. I don't know if you have any other lectures today left. Okay, my advice is for you after the finals, get some rest, but not for long. Repeat what we had covered this semester, because next semester we will start from here. In the first lecture, I will just write down the Maxwell's equations and start using them. So I will not review. The reviewing part was this semester. We reviewed basically what you had learned in the first year, plus with some additional mathematics. I also strongly advise you to read the rest of the book. I'm not asking you to study it in detail. Don't spend time, but just read through it. At least you will know where we will be heading during the semester. I mean, just make it before sleep, your bed book. No computation, no pencils, no pens, etc. It's not necessary. Just read through it. And you will also see what you will need, because next semester we will be doing much more mathematics. There will be much more curls and divergences, etc. So if you have problems with that, review those two. So see you in the exam.